Partial fraction expansion. What's partial fraction expansion? Partial fraction expansion is a method to break down a fraction of two polynomials which have rational coefficients into sum of simpler fractions. It's a math concept, and the idea is that if I have a fraction, I want to break it into two or multiple pieces. Why do we care about it? Because when we have Laplace transforms, we sometimes, as we have seen in the definition of Laplace transform, have scenarios that we have a fraction like this. What's the inverse Laplace transform of g of s here? I have no idea. We don't have it. We don't have it in the table. So we can't just directly find the inverse Laplace transform of this fraction from the table. We have to break it down into simpler terms like this. Then we can find the inverse Laplace transform of g by taking inverse Laplace transform of the first piece, second piece, and then add them up. So let's see this example. We want to take the inverse Laplace transform of s plus 1 divided by s plus 2, s plus 3. If I know that I can break s plus 1 divided by s plus 2, s plus 3 into these two pieces, negative 1 divided by s plus 2, and 2 divided by s plus 3, then from the table I know that the inverse Laplace transform of the first one, the first term, is negative e to the negative 2t, and for the second term is 2 e to the negative 3t. Go look at the table and make sure that you know how to take inverse Laplace transform of a fraction like negative 1 divided by s plus 2. All right, so how do we do this? How do we expand a transfer function into partial fractions? We have three methods. We studied three methods here. The first method is to imagine you have this fraction. You just multiply both sides with the or by the denominator of the fraction. So before doing that, I have a guess that a fraction with s plus 2 and s plus 3 in the denominator probably is going to have one term with s plus 2 in the denominator and another term with s plus 3 in the denominator. I mark the numerator with a and b. These are my unknowns. I want to find a and b. And so in method 1, we just multiply both sides by s plus 2, s plus 3. If we do that, the left-hand side is going to have s plus 1. And what is going to remain from this first fraction, if I multiply it by s plus 2, s plus 3, is a times s plus 3. And for this second term, it's b times s plus 2. Now I factor all terms with s in them and other terms that do not have any s. On the left-hand side, I have 1 s plus 1. Therefore, a plus b should be 1, and 3a plus 2b should be 1. So then I solve this, and I get b is 2, a is negative 1. So that's method 1. You just multiply the denominator with, just multiply both sides with the denominator. Method 2 is to specify values for s and plug them in. For example, say, well, what if s is negative 4? If I know that I can break this fraction into two pieces and I don't know a and b, I can just plug in numbers for s. I can put 0 or I can put 1 or 5 or negative 20 or whatever to have something on some number in the left hand side, and then in the right hand side I would have something with a and b in it. So if I use negative 4, if I substitute negative 4 here, I'm going to have negative 3 divided by negative 2 times negative 1 on the left hand side, which is negative 3 divided by 2. And then on the right hand side, I have negative a divided by 2, negative b. If I plug in negative 1, the left hand side would be 0, The right-hand side would be a divided by 1, which is a, and here I'm going to have b divided by 2. So I can solve for a and b. This is method 2. Method 3 is more complicated, but the reason why we work with method 3 is because you can use it for more complicated terms. If I want to rely on method 1 and 2, meaning that I want to substitute something for s, or if I want to multiply it by the denominator, the problem I have, let me go back, is this. Imagine if rather than having two terms in the denominator, if I had 5. Now I had to write here a divided by s plus 2, b divided by s plus 3, c divided by something, d divided by something, e divided by something. Then if I would multiply both sides by the denominator, I wouldn't get the system of equations with 2 equations. I would get 5 equations. Now how do you want to find that? So you're going to have a difficult, rather, or cumbersome problem to solve. So method 3 has formulas, and for a lot of cases it's simpler. But method 3 itself has 2 cases. Let's focus on simple case, or case 1. Simple case, or case 1, is when you only have simple terms, meaning that the fraction you have only has terms that, so that the denominator only has simple terms, which means the value here, P1, P2, P3, is just by itself. You don't have S plus P1 squared. You don't have multiplicity. If that's the case, and you want to write it down, you want to write f of s as terms, s with s plus p1 in the numerator, s plus p2, s plus p3 to s plus pn, and you want to find a1, a2 to an, you can use this formula. Now, this is a scary looking formula, but if you actually think about it, it's kind of simple. What it's saying is simple. It says if you want to find ak, so one of these numerators, multiply f of s by s plus pk. Okay, ak is the numerator of the fraction with s plus pk in the denominator. So all this is saying is that, do you want to find this term, like a2? Look at f of s, and what does it mean if I multiply fraction f of s with s plus p2? It means that I'm holding my hand, I'm imagining s plus p2 doesn't exist. I'm holding my hand on this term as if it doesn't exist. And then when it says take the limit for s going to negative pk, means that imagine this term doesn't exist, and then substitute the root of it, which is p2 or negative p2, into all other terms. Okay, let me repeat. Or rather, maybe it's better to see an example. Expand the following fraction using Heaviside method. Okay, or method number 3. First, look at f of s. It only has simple terms in the denominator. There is no multiplication. There is no s negative 2 squared, s plus 4 cubed, things like that. So what is my guess about this fraction if I want to break it into pieces? Well, my guess is going to be that there's probably a term with only s in the denominator, another term with only s minus 2 in the denominator, and then a third term with s plus 4 in the denominator. And I want to find these numerators, a1, a2, a3. Okay, if I want to find a1, what do I do? a1 is the numerator of the term with s in the denominator. So I go to my fraction. Imagine s doesn't exist. Imagine just I have only 2 divided by s negative 2, s plus 4. Okay? And then substitute 0, the root of this term, into the fraction. So I'm going to have 2 divided by 0 minus 2 times 0 plus 4. So 2 divided by negative 2 times 4, which is negative 8. So this, what remains is going to be 2 divided by negative 8, or negative 1 over 4. That's what I'm going to get if I actually do the math of this limit, this formula. This formula is exactly doing this. Okay, now try to yourself, before I solve it, find A2 here. How can I find A2? Well, A2 is the numerator of the term with s minus 2 in the denominator. So I imagine s minus 2 doesn't exist. I imagine I have 2 divided by s times s plus 4. Now I substitute the root of this term, which is 2 plus 2. Okay, so I'm just going to substitute that. Numerator has 2. Denominator is going to have positive 2, and then positive 2 plus 4, which is 6. So 2 divided by 2 times 6, what's going to remain is 1 over 6. What are you going to do for this term? What is A3? Well, I imagine this doesn't exist. Then I put negative 4 here and negative 4 here. I'm going to have negative 4 times negative 6, and the numerator is 2. Negative 4 times negative 6 is plus or positive 24. 2 is in the numerator. I have 1 over 12. Okay, that's the simple case. More complicated case is when I have repeated terms. If I have repeated terms, like here I have s plus p to the k, what's going to happen is that when I try to break this fraction into pieces, I might have, I'm going to have the simple terms, right? S plus p1, s plus p2 to s plus pn. For the term that has repetition, I might have any multiplication of it. So in the fraction that when I break it into pieces, I might have s plus p to the k, I might have s plus p to the k minus 1, or I might not have it. I might not have any of these. So we should check. We should really find the values of bk minus 1, bk minus 2 to b1. For other terms, for a's here, a1 to an, we just simply use what we were doing in the previous slide. For these more complicated terms, I have to do this. I have to use formula number 2. Formula number 2 has this term inside, which simply is just saying what the previous slide was saying. So multiply this fraction by s plus pk. Now, what is different here is that now you have to take derivative sometimes. And then you multiply it by 1 divided by this term, k minus l factorial. So if I want to find BL, let's say L is 3. If I want to find B3, I'm going to find 1 divided by k minus 3 factorial, and then I take the derivative, the k minus third derivative of s plus p to the k f of s. Let's see an example. I think an example would really help. I want to break this fraction into pieces using Heaviside method. Okay, so I'm going to have a term with s plus 3, which I want to find the numerator of it. But I have a term here which has a power of 2. When I break it into pieces, I might get a term with only s plus 2 in the denominator, and I might get a term with s plus 2 squared in the denominator. So what should I do here?